Hello everyone, this is Professor Roman. Welcome to the 50th video in my video lecture series, An Introduction to Discrete Mathematics. In this video, we're going to discuss directed graphs and strong connectivity. There are many applications of graph theory in which it's useful to be able to assign a direction to each edge of a graph. And so that leads us to this definition. A directed graph, also known as a digraph, is a graph in which each edge has been given a direction. It's customary to refer to the edges of a directed graph not as edges but as arcs. And an arc that's directed from a vertex U to a vertex V will be denoted by an ordered pair, UV, rather than the set notation we've used for edges in the past. And also I'm going to use this arrow with this little doohickey on the tail to denote an arc from U to V. Just to be clear, I've said in the past several times an edge from U to V or a path from U to V. And that was with the understanding, I hope, that those were not a direction. It was simply a way of expressing the fact that there was an edge, one of whose vertices was U and the other was V. So an edge from U to V is the same as an edge from V to U. But when we talk about directed graphs and arcs, then that has specific meaning. An arc from U to V is not an arc from V to U. They are totally different. A directed graph, if you ignore the directions, what you get is what is called the underlying graph for that directed graph. So for example, here's a directed graph. The arrows indicate the direction of each arc. If I remove the arrows, ignore the directions, I get the underlying graph, which is on the right here. Directed graphs can be used to represent all sorts of important things in applications, like communication systems, where the communication can only go in one direction. Also transportation systems whose routes are one way. For example, if you look at this graph, the vertices could be the intersections. This could be a road map, and all the streets are one-way streets. Some cities have a lot of one-way streets in them, so this kind of directed graph would be useful for urban planning and things like that. Here's an example of a directed graph. It might represent a chess tournament, for example, and if there's an arc from vertex U to vertex V, it means U defeated V in their chess match, that sort of thing. So I'm sure you can use your imagination and think of various ways in which directed graphs could be used in applications. Now, the theory of directed graphs has its own set of definitions. And you're probably saying now, oh no, not more definitions. But these aren't quite as bad as the previous ones. Once you mastered the previous definitions, these are just directed versions of those concepts and those definitions. So, for example, if UV is an arc in a directed graph, then we say that U is adjacent to V, or that V is adjacent from U. Okay. And U would be called the initial vertex or the starting vertex of the arc. V would be the terminal vertex or the ending vertex. As to the degree of a vertex, the in degree, right here, of a vertex V, which I'll denote by INDEG, is the number of arcs in the graph whose terminal vertex is V. So they end at V. They come into V. That's the in degree. And the out degree is similar. It's the number of vertices that leave V, or whose initial vertex is V. And then the degree of a vertex is the sum of the in degree and the out degree. And that's the same as the degree we've been discussing for a while in the underlying graph. If you ignore the directions, the degree is the degree of that vertex. Here's an example. I don't think I need to go through this. This is all pretty straightforward. V3 here has out degree 2, because there are two vertices, there are two edges. I'm doing it myself. There are two arcs that leave V3. As far as in degree, there's 1, 2, 3 arcs that terminate at V3. So the in degree is 3, the out degree is 2. Okay. And that's for vertex V3. In degree is 3, out degree is 2. Also, the notions of walks and trails and paths and circuits and cycles, they all have directed versions. We're going to concentrate only on paths, so it'll be simpler. When we talk about a path in a directed graph, we mean a path in the underlying graph. So it has no direction. But a directed path from a vertex V1 to a vertex Vn is a path. It looks like this in symbols. Each arc points away from the first vertex, the initial vertex V1, toward the terminal vertex Vn. So all of these arcs are pointing from left to right. If there is a directed path from U to V, then we say that V is reachable from U. And that's an important concept for us. As to connectivity, a directed graph D is weakly connected if its underlying graph is connected. On the other hand, D is strongly connected if any vertex in D is reachable from any other vertex. So the definition becomes D is strongly connected if there is a directed path between every pair of vertices. And certainly, if a graph is strongly connected, it's also weakly connected, but the converse does not have to be the case. The fact that a graph, for example, the graph in 224, let's look at that. This is a strongly connected graph. It can take a while to sort out whether that's true or not, and I'm going to discuss that in a few minutes. How do you tell whether a graph is strongly oriented or connected, or whether you can add directions to an undirected graph and make it strongly connected? That's a big deal in graph theory, and I'll come to that a little bit later. This one's pretty easy to tell it's strongly connected because the subgraph on the outside here, this square, all the directions point counterclockwise, so you can get around that whole square. You can also get around the circle, you can get into the circle, and you can get out of the circle. Okay, so you might need to say a few more words about this, but it's fairly evident that it is strongly connected. This guy's not strongly connected. There's no way to get from, say, P2 to P1. You can't even get into P1. If you don't start at P1, you'll never reach P1 because all of the arcs touching P1 are leaving P1. So the in degree of P1 is 0. But the fact that a graph is strongly connected, so for example, for a road map, means that you can get from any location to any other location following the one-way streets. Okay. You may have to go through several other locations first, but there is a connected path of one-way streets taking you from any place to any other place. Here's a directed graph, and let's say each vertex represents a person, and each arc of the form UV represents a line of communication that allows person U to send a message to person V. Now, the fact that this graph is strongly connected means that any person can get a message to any other person, but perhaps through intermediaries. This would apply equally well to the case of countries and communication routes between countries. How do we tell whether a directed graph is strongly connected or not? And this is an important question. Well, it turns out that the method of depth-first search, DFS, can be a big help in determining whether or not a graph is strongly connected. I'm talking about a digraph. So I guess I probably should add that. Okay. So the first step is to modify the DFS method, the direct first search method, to adapt it to directed graphs. And this is really easy to do. It might be a good time, if you are a little vague on the depth first search that we talked about earlier, to go back and refresh your memory on that. But all you have to do is restrict the incorporation of maximal paths into the tree to maximal directed paths. In other words, if you have a vertex that is open, it's not closed, so that there is, in the undirected case, there would be an edge from that vertex that did not form a cycle with what you've already done so far. You can follow that edge and extend the edge to a maximal path. Now it has to be an arc leaving that vertex, and that may be extendable to a directed path that is maximal. You can't go any further in extending the path. So the modification really is quite simple. You just make sure all the paths are directed. And that's the only significant difference between the depth first search for undirected graphs and for directed graphs. And I'll refer to that process as a directed depth first search, or directed DFS. Now, it is important to keep in mind that directed depth first searches don't always produce spanning trees, unlike the case for undirected depth first searches, in a connected graph, of course. If a directed graph should happen to have a vertex without degree 0, in other words, no arcs leave that vertex, it doesn't matter how many arcs enter the vertex, but none leave, then if we tried to start at that, a depth first search, a directed depth first search at that vertex, you can't go anywhere. So you're going to get, your depth first search is going to end with just that one vertex. Okay. So while the difference between an undirected DFS and a directed DFS is just you have to follow the arrows, the consequences can be severe. So I want to describe to you a method for determining whether or not a directed graph is strongly connected. And for that I need a definition. So suppose D is a directed graph. The opposite graph, D op, I'll call it, is the directed graph obtained from D simply by reversing the direction of all the arcs. And here is the test, or a test, for strong connectivity. D is a directed graph and U is a vertex of D. Any vertex you choose. Then D is strongly connected if and only if two things happen. Any directed depth first search performed on D starting at U does in fact produce a spanning tree. In other words, it reaches all the vertices of the graph. Also, the same thing must hold for the opposite graph. Any directed depth first search performed on D op starting at U also produces a spanning tree, so it reaches all vertices. And I think if you ponder this for a moment, it would seem to make sense, but we do need a proof. So let's suppose first that these two properties hold. If T is a directed depth first search spanning tree, then that means that any vertex W in the graph is reachable from U, the starting vertex of the tree, the initial vertex of the tree. And it's reachable, so that means there's a directed path from U to that vertex W. But similarly, for the opposite graph and the opposite directed depth first search spanning tree, any vertex W is reachable from U. This is in the opposite graph. So there's a path from U to W in T op. But that's the same as a path from W to U in T. You reverse the arrows. So each of U and W, U being the initial vertex, W being any vertex, each is reachable from the other. And that implies that D is strongly connected. There's one or two more sentences that you would want to add to this proof, and I'm going to leave that for you to fill in because it's good practice. For the converse, we suppose that D is strongly connected. The original justification for undirected graphs, that a depth first search produces a spanning tree, can be modified with not too much trouble at all to the case of a directed depth first search for both D and D op. And I'm going to leave that also for you to ponder because I think it's good practice. Let's try some examples. Here is a directed graph. A depth first search, a directed depth first search of that graph is shown here. So we've got the bold edges will form a directed depth first search. If we start at U here, well, actually I guess I've labeled it, well, U1 I've also labeled it V. We have to first find a directed maximal path. So follow F1, then F2, then F3, and now we've got a choice here. We could go to we could go through F8 to U9 here, or we could have gone this way, but we can't do both, one or the other. So we get a maximal path, let's say ending here. We back up. This is another maximal directed path, I should say. Come back here, and a final directed, maximal directed path, and that gives us our directed depth first search. Always following in the direction of the arrows. The opposite graph is shown here. So all the arrows, for example, this arrow is now reversed to this arrow. This one gets reversed to this. All the arrows are reversed. That's the opposite graph. And this is a directed depth first search. In the opposite graph, you can see it's different. I started from V and I went down here rather than going up. So this is a directed depth first search that produces a spanning tree in D-op. I didn't say this is a spanning tree. The bold edges and vertices form a spanning tree. Okay, so does this. So we have spanning trees for both D and D-op, which according to the theorem means that this is strongly connected. Okay, so it might be worth thinking here about how else you could show that this was strongly connected. Of course, the brute force method would be to look at every pair of vertices and try to find a directed path between them in both directions. 3, 4, 5, 6, there are 9 vertices. So 9 choose 2 is what? 9 times 4 is 36 different pairs of vertices. You'd have to find 2 paths, 2 directed paths for each of those 36 pairs. Not a very pleasant prospect. It's clear even from this relatively small example that using a depth first search is much better than trying to do it by just brute force. Here's another example. This is a directed graph. Here is a depth first search starting at V. This depth first search does reach all the vertices. So it is a depth first search spanning tree. This is the opposite graph, and we have a depth first search starting here, goes along here, and goes up to here. We get stuck. This vertex is closed. We can't take this edge because it's going in the wrong direction. So we back up here. This is closed. We can't take this. Well, that would create a cycle anyway. This would also create a cycle. So we back up. And by the way, when I say cycle, I mean directed cycle. Okay. So we back up to here, no place to go, back up all the way. So this is a directed depth first search, but it doesn't produce a spanning tree. This vertex is not included in the tree. So we can conclude then that this is not strongly connected. Okay. That's apparent that this vertex is a problem because its out degree is 0. But if this had been a much more complicated graph, it might have been difficult to spot that. One thing you could always do, if you wanted to, was check each vertex for its in and out degrees. If you find a vertex where one of those degrees is 0, you know you're in trouble. But you might not, and the graph still might not be strongly connected. Okay. Well, now we come to our most complex issue, and that is orientability. An undirected graph G is said to be strongly orientable, or sometimes just orientable, if it's possible to assign a direction to each of the edges of G in such a way that the resulting directed graph is strongly connected. And that assignment would be referred to, naturally enough, as a strong orientation of the graph. So just a very simple example. This graph here is not strongly orientable because it has this bridge here, and you can only assign this bridge one direction. If you assign it to go from left to right, then there's no way for a vertex on the right to reach a vertex on the left because it can't cross this bridge. It's a one-way bridge. This map might show you an example of why the issue of orientability is important. Suppose this is a street map of a certain kind of bizarre town, and all the streets are two-way streets. But the city government has decided that it wants to make all the streets one-way because, in general, it feels that one-way streets are safer than two-way streets. A lot of children in the area, they want to cut down on possible traffic problems. Well, can you do that? Can you orient this graph so that you can still reach from any location to any other location following one-way paths, one-way streets? So the question comes down to, is this graph strongly orientable or not? A graph G is strongly orientable if and only if it is connected and has no bridges. We've already seen the trouble that a bridge can cause, and that would apply to any graph. Okay. So if a graph has a bridge E, then the removal of E would create two additional connected components. Well, if it's connected, it would be two components. But we still have this problem that E can only be oriented in one direction. And so if it goes from a vertex in H to a vertex in K, then the vertices in K can't reach the vertices in H because they'd have to go the wrong way along the one-way bridge. So if G is strongly orientable, it cannot have any bridges. As to the converse, we suppose that G has no bridges, and we want to show there is a strong orientation. And this picture here will help with that. So this is one way to approach this proof is to suppose that H is a maximal subgraph of G, this ordinary subgraph, with respect to being strongly orientable. Okay. There will be such a thing. An individual vertex is a subgraph. It's strongly orientable. Graph has no bridges, so every edge is in a cycle. Cycles are strongly orientable. So there will be strongly orientable subgraphs. Take a maximal one. You can't enlarge that subgraph with additional edges or vertices and still have a strongly orientable subgraph. Okay. Well, that implies that all of the edges of G that connect vertices of H are included in H, because otherwise including that edge would not break the strong orientability. Put another way, if the vertices of an edge are already in H, then you can put the edge in H as well. It's not going to break strong orientability. Now, if H happens to be all of G, of course, we're lucky and we're done. So suppose there's a vertex, I'll call X, that's not part of H. Well, since G is connected, there's got to be a path from X to some vertex in H. In fact, to any vertex in H, but let's just say some vertex in H. And so it follows there's a vertex that's not in H that has an edge, which I called E, and I've shown it here. It goes from V to a vertex in H. There's a path that does it. The last edge in that path, so to speak, is an edge that connects a vertex that's not in H to a vertex that's in H. Okay, now since G has no bridges, then there must be a cycle in, call it C, I called it C, that contains the edge E. And I've drawn a picture of that here. Okay, it's the red and the blue edges. And the portion of that cycle that's not in H, the edges are not in H, that's the red portion I call P. Okay. Now, we can orient P to a directed path from W here to U. In either direction, doesn't matter. So we form a directed path. Now we can incorporate P into H. It's really the same reasoning that allowed us to incorporate an edge whose vertices were in H into H if it wasn't already there. So let me go back then to that. Suppose that there was an edge in G that went between these two vertices. Then you could have expanded H to include that edge. It would still be strongly orientable, strongly connected. But H is supposed to be maximal, so there were no such edges. Okay. Well, the path works the same way. This is a directed path. We could incorporate it into H, and we would still have a strongly orientable subgraph. Okay. Well, that contradicts the maximality of H. And so that's not possible. The only assumption we made was that there was a vertex X that's not part of H. That's false. H, a maximal subgraph that's strongly orientable, has to be all of G. And that's the proof. You might want to stop and take a deep breath. The problem with this proof, it's perfectly correct, is that it's not algorithmic. We check this graph. We have a connected graph. We check it. It has no bridges. We know it's strongly orientable, but this doesn't tell us how to get a strong orientation, how to orient the graph to make it strongly connected. So let's look at that. Now, the way I'm going to do this is to use a depth-first search tree. And I need to make a few more comments about depth-first search trees in general for arbitrary graphs. Here is a portion of a depth-first search tree conducted on a graph G. Starts with the initial vertex. The green edges here form a maximal path. That would have been the first step, or at least one choice for first step. And this vertex, being an end vertex, is closed, so we back up to here and we head out along another maximal path. That's the blue path here. We have to back up. We come to V. V is not closed. We can go down, well, we can go to cyan and then eventually back red to the end, eventually back 1, then orange, then continue back all the way to U. Okay. So that would be a complete depth first search for this graph, but this could even just be a portion of a bigger depth first search graph. It doesn't matter. Now, consider two vertices here, x and y, in this depth first search tree. There are two possibilities with regard to the parent-child relationship between these two vertices. One possibility is that one of the vertices is an ancestor of the other, so it lies on the unique path from U to that first vertex. That's not what's happening in this picture. But for example, if you look at this vertex here, it is an ancestor of Y. So is V. V is an ancestor of Y because the unique path from U to Y contains V. Now, the other possibility, if neither of the vertices are ancestors of the other one, then that's the case for X and Y, then the vertices have what I will call a closest common ancestor. And that's the vertex V, and it is V in this picture as well, that is farthest from the initial vertex, but lies on both of the unique paths from U to X and from U to Y. So we just start at U and we follow the unique path to X and to Y. Two paths we're following. They both start at U. They may remain the same for a certain distance, but eventually they will break apart because neither vertex is an ancestor of the other. As soon as they break apart, they will stay broken apart because there are no cycles in a tree. And so we have this situation where X lies on, in this case, the cyan path, and Y lies on the red path. So that's the only other alternative. Now, what can we say about this closest common ancestor V? Well, it's not an end vertex because we can't, if it was an end vertex, X and Y would have to be the same vertex, which they're not. V was incorporated into the depth first search tree. Like all vertices, the way they get incorporated is because they lie on a maximal path. So in this case, it was the blue path. After we added the green path to the tree, we backed up to here and we added the blue path. And that's when we picked up V. Remember, focus will go all the way to the end, but we're not talking about focus. We're simply talking about what gets added to the tree. Everything on this blue path is added. And it's added, there's a timing issue here that's important. It's added after the green path, but before either of these two other paths, cyan and red. At the point when V was marked closed, the vertices x and y had already been incorporated into t from different maximal paths starting at v. So after the blue path is created, focus is down here. If this was the whole tree, we'd be backing up to here, then up to here, then to v. And we notice that v is not closed because it has, in fact, two edges we could follow to form new maximal paths. So we're going to follow one of them, maybe the cyan path, eventually, and that means we'll pick up x into the tree. We'll eventually have to go back up to v another time, and we can follow the red path. We'll pick up y, back up, follow orange, back up, keep backing up, and you're done. So what has happened is that between the paths that pick up x and y, one of them happened first. Could have been either one. In fact, the choice could have been made either way. Once we were finished with the blue path and we're back up to here, we could either start the path with the cyan edge or the red edge. But one starts before the other. And in some sense, one finishes before the other one starts. Okay? And I'm going to assume the cyan path came before the red path. Now, after this maximal path, p sub x, that's the one that contains x, the cyan path, that starts at v, was incorporated into the tree, the algorithm will eventually mark all the vertices on that path as closed, and that would include x, will be marked as closed, before the focus returns to v again. That's how the depth first search works. Once you leave v along an edge, like the cyan edge, you come down to the bottom, the focus, you back up. There may be a bunch of other stuff branching off of this cyan, the cyan path, several other maximal paths, only finitely many because the graph is finite. But eventually you will finish all the incorporation you can do starting from a vertex on the cyan path and have to come back to v. At that point, when this whole section of the tree is finished and everything that comes off of it is finished, now you can follow the red path. Okay. So x is closed before the red path is even started, right? Well, what does that mean? It means that there can be no edge E from X to Y. That's this edge that I wrote as a dotted line. Because if there was such an edge, it would have been used during our processing of the tree on the cyan path. We would have, let's suppose this edge was here. We go down the cyan path, the red path doesn't exist yet. As soon as we create the cyan path, we go to the end vertex. Eventually, we're going to back up to X. X got closed at some point because this edge would have been followed. It might have led to a further, it could have come, then you would have come down here or over here or somewhere. But the point is, this edge, if it had existed, would have been incorporated into the tree before the red path was created. So Y was an available vertex. E would have been an available edge to create a maximal path starting at x. Okay. This is something you may need to think about, replay the video. But no edge can exist between vertices on different paths because of the timing issue. One path is created before the other. That edge would have been used up by the first path, and then the second path would not have been possible, would have created a cycle. Okay. So the consequence of this delicate argument is that all back edges in G, edges that are not part of the tree, must be of the form AB, two vertices A and B, where one of the vertices is an ancestor of the other. So if you come back here, there could be a back edge from this vertex to this vertex, or even from this last vertex up to this vertex on the same path. Okay, there could be an edge from V to this last vertex. That is acceptable because V is an ancestor of this last vertex. So this has profound consequences for what we're trying to do, because it means that a back edge forms a unique cycle. It's got to be part of a cycle because there are no bridges. A unique cycle, all of whose other edges lie in the tree. So if there is an edge from, let's say, this last vertex here to this vertex, it obviously forms a little triangle, all of whose other edges, both other edges, are part of a maximal path. They're in the tree. So with this in mind, consider the unique path from the initial vertex U to some vertex W. Could be any vertex. We could extend this path from W following following edges until we reach a leaf. This is still undirected. This is just an undirected graph. Okay. Now, since G has no bridges, this edge here has to lie on a cycle, call it C. That cycle must contain a back edge because you can't form a cycle with just edges from a tree. Where must that back edge stretch? Well, one of its vertices, it has to be on the cycle with this edge, and it has to contain only edges from this path, other than the back edge. So one of its vertices has to be either W or one of these X's, the descendants of W. And the other edge has to be either VK or one of its ancestors. VK and its ancestors are ancestors of W. So this back edge has to connect W or one of its descendants with an ancestor of W. Okay? So again, we've shown that for any vertex W, there is a back edge of G, it's not part of the tree, that connects either W or one of its descendants, one of the X's, to an ancestor of W. Now we can define a strong orientation. Orient each edge of the depth first search tree so that it points away from the initial vertex u. So if xy is an edge and x is closer to u, orient the edge from x to y, from parent to child. I should have said that, parent to child. Orient all the back edges so they point toward the initial vertex. This is a strong orientation because there's a unique path in T from U to any vertex in G. That's what a depth first search spanning tree does. So every vertex W in G can be reached from the initial vertex U. But that's one direction. That's reachability from U to any place else. But for any vertex W, there's a back edge from W or from one of its descendants to an ancestor of W. That means that some ancestor of W, call it W prime, is reachable from W. We're backing up now. We might have to start at W and go further away until we hit the vertex of that back edge. Or it might be right out of W. But then when we follow the back edge, we come out, so to speak, ahead of W, an ancestor of W. So this is how we back up from a child, from a vertex to an ancestor of that vertex. So you can't do that on the tree. They're all pointing in the wrong direction. But the back edge will get you there. Well, once you got from W to an ancestor of W, you can do the same thing for the ancestor, back up to one of its ancestors. Eventually, you will back up all the way to U. So any vertex W will reach U. And that's how we go the other direction, and we get a strong orientation. Okay. We're almost done. Here's the algorithm then. Let G be a strongly orientable graph with n vertices. I don't even know why I said that. Okay. Strongly orientable graph. I had another algorithm for this. You'll find it common if you look in other sources of literature. The way this is done, the way depth first searches are done is as you incorporate vertices, you label them and you do it with an index. So V1, V2, V3, V sub 1, V sub 2, and so on. And then you can use the indices to describe how to back up and things like that. But I decided not to do it that way. So that's why I had originally done something like that and didn't like it. So that's why it was important to know there were n vertices. But now it's not. So let G be a strongly orientable graph. The following procedure will produce a strong orientation. Construct a depth first search spanning tree and orient all of its edges from parent to child. Orient all of the edges that are not in T, the back edges, from descendant to ancestor. And that's what we just got through explaining will give a strong orientation. So here's an example. A graph here, strongly orientable. Is connected and has no bridges. So we know it's strongly orientable. First, we perform a depth first search, starting at V here. So that takes us, say, along the blue maximal path, backing up, pick up the red maximal path. Orient everything, all the edges on the blue path, away from V. So this way, this is parent to child, parent to child, parent to child. Parent to child, parent to child. There are 3 back edges, go from child to parent. Actually, well, no, I'm sorry, not from descendant to ancestor. Descendant to ancestor. You follow this path along here. This vertex is a descendant of this vertex. Okay. Descendant to ancestor, descendant to ancestor. And this is a strong orientation. Okay, we are done with this material. What's next? Directed networks and the shortest path problem. And I believe that after that is a long section. That may take a couple of videos. Finite state machines, and that's the final section of the book. So we're closing in on it. Thank you for watching. Hope to see you in the next video.